Hi, we are going to do an experiment here, and I have a copper penny. So this is from before 1982, pure copper, and this is like number 9 in your homework packet. It's kind of this demo to go with this. I think I did it in one of the other worksheets. I'm going to take this copper penny and I'm going to put it in this nitric acid. This is the 15.8 molar nitric acid. So I'm going to put this in here and it's going to start bubbling. It's bubbling kind of a greenish color. Oh, look at that. There's red smoke coming out of there. And notice, so now it's bubbling green. There's red smoke. The red smoke is going up through this tube and going into this container, which I'm realizing it's not in very good view. So I got to move this a little better so you can actually see it. And it's going into this pink container here. Now this pink container has water, and then it has it has water and there's a little bit of phenolphthalein and ammonium hydroxide. And that ammonium hydroxide is a base, okay? And then phenolphthalein will turn pink in the presence of that base. So we're gonna see if anything happens to this right here, which gives us a little bit of stuff. This reddish gas, that's why I've got it looped in here, is nitrogen dioxide, and it's a toxic gas. So that's why I have all this stuff wrapped up in here, so that's not going all over the place right here. So we're gonna do this and keep that going here. And I'm going to feel this now, and I start to feel it pretty warm, okay? So this is like a lot of chemical reactions, an exothermic reaction. Now notice what happened here is that this turned clear. So let's see, it was a base, but now it's turning clear. So maybe this reddish gas might be acidic because it's making the phenolphthalein turn from the pink back to the clear and tending to neutralize that out. Okay, I could look at an equation. It looks like it's still bubbling through right there and definitely getting warmer right now. So I can feel that. And we can look at this reaction. And I think I'll do that right here. I think I'm going to move this computer over to right here. And you have this equation, page 9 in your homework packet. We'll see how that goes. I don't know if you can see that very well or not, but I'm taking copper and I'm combining it with HNO3, which is nitric acid, which is a strong acid. And this NO2 gas is a nitrogen dioxide gas. That's that reddish amber hue that you see. So like sometimes under real intense heat and pressure, you could take nitrogen out of the atmosphere and burn that and you could get NO2 gas, like in a car engine. And then you look over the city, like the amber hue kind of over the city in the summer. Sometimes you can see that. That would be nitrogen dioxide. Okay, you probably see it more in bigger cities there. Then we're getting copper 2 nitrate. No evidence of that yet, but we'll look for that coming back. And then we got some H2O. So you have this balanced equation. It's pretty complex. There's a single displacement to some extent, but then there's a breakdown of a gas and a decomposition. So we have a few things going on right here. Okay, I'm going to put the thing back over here and where we were originally. Let's see how this looks. All right, we can see, I think, everything right here. And let's see. So it looks like it's almost finished bubbling. This is quite warm right now. I didn't get a temperature of it, but it definitely feels warm to the touch. And that's our reaction. Yet something else is going to happen here. So what are we going to do to pass the time as this goes? I guess I could probably pause it and have you come back, or you could fast forward, I guess, to see the end. Or we could hear about the Ira Remsen story. And Ira Remsen was a 19th century professor. So it was at 1800s at Johns Hopkins. And he was a chemistry professor. And he writes in his memoir, probably when he was quite a bit younger. So he read something in a textbook of chemistry before he even became a chemistry person, and it said nitric acid acts upon copper, like ACTS, and then upon copper. And I was getting tired of reading such absurd stuff, and I was determined to see what this meant. Copper was more or less familiar to me, for copper scents were then in use. I had seen a bottle marked nitric acid on a table in the doctor's office where I was doing time. So I think he was doing time because you go in the little waiting room and then they just wait for the doctor. And sometimes it takes a long time. So he's looking through all the stuff there, and then he decides to do an experiment. I didn't know the peculiarities, but the spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the word acts upon meant. So again, he's doing this in the doctor's office while he's waiting. The statement nitric acid acts upon copper would be something more than mere words. All was still. To the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened up the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. Well, but what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A green-blue liquid foamed and fumed, just like we saw over here, and a reddish hue covered everything. The air in the neighborhood of the performance became colored dark red. A great colored cloud arose. This was disagreeable and suffocating. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out of the window. A new observation that nitric acid does not only act upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my pants, and another fact was discovered. Nitric acid acts upon pants. Taking everything into consideration, this was the most impressive experiment and relatively probably the most costly experiment I have ever performed. It was a revelation for me, and it resulted in my desire to really, on my part, to learn more about this remarkable kind of action. And plainly, the only way to learn about it was to see the results, to experiment, to work in a laboratory. And then I think he got into chemistry, and that was his motivation. And I'm not encouraging you to do that when you go to the doctor's office. You take the bottles and try stuff. But that's one thing that I guess motivated this gentleman back in the 1800s. Okay, so we're almost done here. But what's happening here is this right here looks like it's done, but something is happening. There's water and it's starting to move back up here. Okay, in fact, it's right about here right now, and it keeps climbing up. And why does it keep climbing up? We created a pressure differential. So what's the pressure differential? Well, where is the pressure greater? In the room or coming out the tube? Well, it's being forced up through the tube. So somehow we're creating a force going this way. Essentially, you can think of it as being a suction, but essentially there's an absence of pressure here and in this system here. And what's happening is the room pressure is forcing it up back this way. We're about right here right now. So this was hot and it was still spewing out bubbles right there. But when it was done spewing out bubbles, it was real hot. The molecules are moving real fast. But then it got sealed off because bubbles weren't coming out anymore. And now the temperature is dropping back down because the reaction is done. So the reaction's done and it's starting to cool down, meaning the molecules are moving more slowly, striking the sides of the container with less force and less often. And that's causing the pressure to decrease in here relative to the outside pressure. Because of that, the pressure on the outside is able to push on here and force water up to this point right here. Well, I think we got to try to stretch this a little bit further. We're here. It's got to get up to here. And then what's going to happen when it gets here? I think we'll watch this and we'll just see. Okay, so now we're about here, again, gradually pushing up and working its way until we get to the spot right here. Okay, now we're right up here. Little status check. Maybe we need to get more mold day jokes. No, I think that's probably okay. I'd say it's going to be about 1 more minute. So I went fast forward too quickly. Let's see, it's right here. Yeah, we're going to happen in the next, going pretty quickly right here. So there's the water and it just kind of keeps going here. Okay. Anybody go out like siphoning gas? Okay. Don't recommend doing that. Okay. But kind of that same principle we got going on here. Okay, we're right here. Probably what, 30 seconds? I guess that was a long minute. So probably about 30 seconds till we see some action. I think I'm going to rinse this out. Hopefully I won't miss it. Okay, now we're right here. Got the long 10-second countdown. 10, 9, 8, 7, 6, 5, 4, 3, here it is. 2, the water's starting to go. Let's see what happens. Oh, look at that blue. It's the copper +2 solution. And where's my penny? It's all part of the copper +2 solution, which is the copper nitrate right there. So copper, no charge to +2, was oxidized. I think you'll find that the nitrogen in this equation is actually reduced to compensate for that. And there is our reaction for number 9. Thanks for watching.